Ray Doyle's hands were covered in metal shavings when he saw it, a hairline fracture spreading across the wing joint like a spider's web of death. The P-51 Mustang on the assembly line wasn't supposed to crack, not here, not during routine testing. Engineers were already screaming about production quotas while pilots were dying over Europe because their wings were folding mid-flight. Ray had a solution, but it involved drilling a hole where no blueprint said to drill, inserting a screw at an angle that would make any engineer's skin crawl. His foreman called it stupid tinkering. The brass called it insubordination. But when test pilots pushed those fighters to 8 Gs and the wings held, when squadrons started coming home instead of spiraling into the English Channel, everyone had to admit that sometimes the best ideas come from the factory floor, not the engineering department. Before we carry on, please hit the subscribe button to make my day, and let me know where you are watching from in the comments. The North American Aviation Plant in Inglewood, California, stretched across acres of concrete and corrugated steel, a cathedral of American industry that never slept, never stopped, never gave the enemy a moment's rest. It was October 1944, and the war in Europe was entering its critical phase. Every Mustang that rolled off the line meant one more fighter to escort bombers deep into Germany, one more chance to bring boys home alive. Ray Doyle had been working the night shift for 16 months straight, his fingers permanently stained with cutting oil, his back aching from hunching over drill presses and lathes. He was 38 years old, too old for combat duty, but young enough to feel guilty about it every single day. He had grown up in Peoria, Illinois, the son of a railroad machinist who taught him that metal had a language if you learned to listen. His father used to run his fingers across steel joints and hear stress points that engineers missed, feel vibrations that indicated weakness long before catastrophic failure. Ray inherited that gift, though he never called it that. To him, it was just common sense, the kind of knowledge that came from paying attention instead of assuming the blueprint knew everything. When he moved to California in 1942, chasing defense work and better wages, he brought those lessons with him. The factory supervisors saw him as just another pair of hands, another body to fill a spot on the assembly line. They had no idea he was about to save thousands of lives. The problem started showing up in late September. Mustangs returning from high-altitude combat missions over Germany were developing stress fractures around the wing root attachments, right where the wing joined the fuselage. It wasn't every plane, maybe 1 in 20, but that was enough to kill pilots and lose expensive aircraft. The Army Air Forces sent urgent cables demanding fixes. Engineers from North American's Design Bureau descended on the factory floor with clipboards and slide rules, measuring tolerances, checking metallurgy reports, running calculations that filled blackboards with incomprehensible equations. They concluded the problem was in the heat treatment of the aluminum alloy, or possibly in the riveting sequence, or perhaps in the torque specifications for the attachment bolts. They issued new directives, modified procedures, added inspection steps. The cracks kept appearing. Ray first noticed it on a fuselage that came through his station on a Tuesday night. He was responsible for final inspection of wing attachment points, a job that required him to physically crawl inside the fuselage with a flashlight and magnifying glass, checking every rivet, every bolt hole, every weld. Most inspectors hated it, the cramped quarters, the metal edges that scraped knuckles raw, the claustrophobic darkness. Ray found it peaceful. Inside the belly of a fighter plane, with only his flashlight and his thoughts, he could focus completely on the metal, let his fingers trace the joints, feel for anything wrong. That night, his fingers found something very wrong indeed. The crack was barely visible, thinner than a human hair, running at a 45-degree angle from the primary attachment bolt. Ray marked it with chalk, backed out of the fuselage, and called over his supervisor, Frank Brennan. Frank was a good man, former Navy machinist who knew quality when he saw it, but he was also under tremendous pressure to keep production moving. He looked at Ray's chalk mark, pulled out his own magnifying glass, and swore quietly. This was the 3rd cracked fuselage this week. If they scrapped this one, they would miss their quota. If they let it through, it might kill a pilot. Frank made the only decision he could. He red-tagged the fuselage, pulled it from the line, and sent an urgent memo to the engineering department. The engineers arrived the next morning, a delegation of 5 men in white shirts and thin ties, looking exhausted and irritated. They measured the crack, took photographs, filled out paperwork. The lead engineer, a man named Harrison with round spectacles and ink-stained fingers, delivered his verdict. The fuselage was scrap. The crack indicated a fundamental flaw in the casting, probably a void in the aluminum that compromised structural integrity. Nothing could be done. Build a new fuselage, stick to the specifications, hope for better luck next time. Ray listened to this explanation while cleaning his tools, and something about it bothered him. The crack wasn't in the casting itself. It was in the area around the bolt hole, where stress is concentrated during flight. It looked like a fatigue crack, the kind that developed over time when metal was asked to flex in ways it didn't want to flex. That night, Ray stayed late, off the clock, studying the rejected fuselage. He brought his own tools, his own lights. He wanted to understand what the metal was trying to tell him. The Mustang's wing attachment design was elegant in theory, a series of heavy bolts passing through reinforced lugs that distributed flight loads across the fuselage frame. But elegance in theory didn't always translate to reality. Ray noticed that when the wing flexed under G-forces, which it had to do, or it would snap like a brittle stick, the primary attachment bolt became a fulcrum point. All that bending stress concentrated right where the bolt passed through the aluminum, creating a pressure point that the metal couldn't handle indefinitely. The engineers had calculated the loads, specified the materials, but they had treated the wing as a static structure. Ray knew better. Wings were alive, breathing things that twisted and flexed and absorbed punishment. They needed to move, but they also needed support where movement created stress. He thought about this problem for 3 days, working his regular shifts, inspecting fuselages, watching crack after crack appear in the same location. The engineering department tried various solutions, none of which worked. They specified harder aluminum alloys, but those were brittle and cracked faster. They added reinforcing plates, but those added weight and created new stress points. They modified the bolt torque specifications, but that just made the attachments looser and more prone to vibration damage. The cracks kept coming. Production slowed, memos flew. Officers from right field arrived to observe the problem firsthand. Everyone had theories. Nobody had answers. Ray's answer came to him on a Sunday afternoon while he was fixing his neighbor's fence. The fence post had split near the base where it entered the ground, right at the stress point where wind leverage concentrated. Ray's neighbor wanted to replace the whole post, but Ray had a different idea. He drilled a small hole at an angle through the split, inserted a lag screw that pulled the split sections together while also redirecting the stress into the undamaged wood below. It wasn't pretty, it wasn't by any book, but it worked. The fence stopped wobbling, the post stopped splitting. Ray stood there looking at his crooked screw and thought about wing attachments. Monday morning, he came to work early before his shift started. He found Frank Brennan in the supervisor's office, knee-deep in production reports and looking like he hadn't slept in days. Ray asked permission to try something on one of the rejected fuselages, something experimental. Frank looked at him with bloodshot eyes and asked what kind of experimental. Ray explained his idea. He wanted to drill a small auxiliary hole, offset from the primary attachment bolt, angled at about 30 degrees, and insert a support screw that would help distribute the flexing load. Frank stared at him for a long moment, then asked if Ray had lost his mind. The blueprints didn't show any auxiliary holes. Engineering hadn't approved any modifications. Drilling holes in airframe structures without authorization was grounds for immediate termination, possibly even sabotage charges in wartime. Ray understood all that, but he also understood that pilots were dying because wings were failing and nobody else had a solution that worked. He offered a compromise. Let him try it on a fuselage that was already rejected, already headed for scrap. If it didn't work, they lost nothing. If it did work, they might have something worth showing the engineers. Frank considered this, weighing his career against the possibility of actually solving the problem that was threatening to shut down Mustang production entirely. He made a decision that took more courage than most people would credit. He gave Ray 4 hours, off the books, to try his stupid idea. Ray chose his tools carefully. He needed a drill bit small enough not to compromise the fuselage structure, but large enough to accept a screw that could actually bear load. He measured 3 times, marked his spot with a center punch, and started drilling. The bit cut through the aluminum with a high-pitched whine, throwing spirals of silver metal that caught the overhead lights. He worked slowly, carefully, making sure the angle was precise. 30 degrees from vertical, offset 2 inches from the primary bolt, positioned to intercept the stress lines he had traced in his mind. When the hole was complete, he tapped it for threads, cleaned out the shavings, and inserted his screw. It was a standard aircraft bolt, nothing special, but he torqued it to exact specifications using a calibrated wrench that he had checked and rechecked. The screw went in crooked, exactly as he intended. It looked wrong, amateurish, like something a farm mechanic would cobble together in a barn. Frank came by to inspect it, took one look, and shook his head. He told Ray it looked stupid, that no engineer would ever approve something that violated every principle of symmetrical load distribution, that Ray had probably just wasted 4 hours in a perfectly good screw. But he also told Ray to test it anyway, because what did they have to lose at this point? Testing meant mounting a wing to the modified fuselage and subjecting it to load simulation. Ray recruited 2 other machinists from his shift, men he trusted, and they worked through their lunch break to bolt a wing assembly to the fuselage. They used a hydraulic ram to simulate G-forces, gradually increasing pressure while Ray monitored the attachment points with strain gauges he borrowed from the engineering lab. At 2 Gs, nothing happened. At 4 Gs, the structure flexed normally. At 6 Gs, which was beyond what most combat maneuvers required, the primary bolt showed stress, but the crack didn't propagate. The offset screw was doing its job, carrying enough of the load to prevent the concentrated stress that caused failure. At 8 Gs, which was beyond design specifications, the wing bent alarmingly, but held together. The crack that had doomed this fuselage, the hairline fracture that made it scrap, stopped growing. Ray couldn't believe it. Frank couldn't believe it. The 2 machinists couldn't believe it. They ran the test 3 more times with identical results. The stupid crooked screw was working. It was redistributing the stress load in a way that the engineers' calculations had never predicted, creating a secondary support point that allowed the wing to flex without concentrating all the pressure on the primary bolt. It was simple, inelegant, and completely effective. Frank immediately called the engineering department. The engineers arrived an hour later, led by Harrison, the same man who had condemned the fuselage as scrap. They examined Ray's modification with barely concealed contempt. Harrison called it unauthorized alteration of approved designs. Another engineer called it cowboy mechanics. A third pointed out that drilling holes in airframes without stress analysis and metallurgical testing was exactly the kind of stupid tinkering that caused planes to fall out of the sky. Ray listened to all of this without arguing. Just pointed to the test results. The wing had held to 8 Gs. The crack had stopped propagating. Whatever they wanted to call it, it worked. Harrison refused to even consider it. He explained in the tone of someone addressing a slow child that aircraft engineering was a science based on rigorous mathematics and proven principles. You didn't just drill random holes and hope for the best. Every modification had to be analyzed, tested, validated through proper channels. Ray's screw violated load symmetry, created an unanalyzed stress point, and introduced variables that could cause unpredictable failure modes. The fact that it appeared to work in one crude test meant nothing. Harrison ordered the fuselage removed from the test rig, the modification documented as an example of what not to do, and Ray given a formal written warning about unauthorized modifications. Then the engineers left, taking their clipboards and their certainty with them. Frank was furious, not at Ray, but at the engineering department's refusal to even investigate a potential solution. He knew the test results were legitimate. He had seen the strain gauge readings. Ray's modification worked, and dismissing it as stupid tinkering was bureaucratic cowardice. But Frank was also a realist who understood factory politics. Engineers had authority. Machinists didn't. That was how the system worked. He told Ray to forget about it. Get back to his regular inspections. Let the brass figure out their own problems. Ray nodded, said nothing, and went back to work. But he didn't forget. Over the next 2 weeks, Ray inspected 47 fuselages. 19 of them showed stress cracks around the wing attachments. 19 out of 47, a failure rate approaching 40%. Some cracks were microscopic, barely detectable. Others were clearly visible, obvious precursors to catastrophic failure. Every one of them ended up scrapped, pulled from production, replaced with new fuselages that would probably develop the same cracks eventually. The waste was staggering, not just in materials but in time. Each scrapped fuselage represented days of work, hundreds of man-hours, resources that could have gone to building additional aircraft. And while the factory struggled with quality control, pilots over Europe were flying Mustangs with wings that might fail at any moment. Ray thought about those pilots constantly. He had a nephew, Danny, who was a waste gunner on a B-17 flying out of England. Danny's letters home talked about the relief crews felt when Mustangs showed up to escort them over Germany, how the sleek fighters drove off German interceptors that would otherwise tear bomber formations apart. Mustangs were saving lives every day. But if those Mustangs had bad wings, if they failed during combat maneuvers, then American pilots were dying because of a problem Ray knew how to fix. That knowledge ate at him. In early November, everything changed. A Mustang from the 357th Fighter Group, based in England, went into a high-speed dive to intercept a German fighter. At around 7,000 feet, pulling out of the dive, the left wing separated from the fuselage. The pilot, a captain from Pennsylvania with 200 hours of combat time and 6 confirmed kills, died instantly when his plane disintegrated. The wreckage was recovered, shipped back to the States, and delivered to North American Aviation for analysis. Engineers swarmed over the fragments, and what they found terrified them. The wing had failed at the primary attachment point, exactly where factory inspectors had been finding stress cracks. This wasn't theoretical anymore. This was a combat loss directly attributable to a structural defect they couldn't solve. Army Air Force's investigators descended on the Inglewood plant. Production was halted. Every Mustang on the line was grounded for emergency inspection. Officers demanded answers. North American's executives demanded answers. The engineering department had no answers to give. They had tried everything they could think of within accepted design parameters, and nothing worked. The cracks kept appearing. Wings kept failing. People were dying. In the conference rooms and offices, panic was setting in. Frank Brennan, who had kept quiet about Ray's modification for 2 weeks, decided he was done being quiet. He went directly to the plant manager, a tough old bird named Coleman, who had built Liberty engines during the First War, and told him there was a machinist on the night shift who might have a solution. Coleman, desperate enough to listen to anyone, told Frank to bring the machinist to his office immediately. Ray walked into that meeting wearing his work clothes, still covered in metal dust, facing a room full of men in suits who looked at him like he was a janitor who wandered into the wrong building. Coleman asked him to explain his idea. Ray did, using simple language, no technical jargon. Just describing how stress concentrated at the primary bolt and how an offset support screw could redistribute that load. The executives looked skeptical. The engineers looked offended. Harrison started to object, but Coleman cut him off. Coleman wanted to know if Ray had tested this idea. Ray said yes, off the books, on a scrapped fuselage. Coleman asked for the test data. Frank had kept everything, the strain gauge readings, the load measurements, photographs of the crack that stopped propagating. He spread it all across Coleman's desk. The room went quiet as people studied the numbers. One of the Army investigators, a major with engineering training, asked several technical questions. Ray answered them all. The major looked at Harrison and asked why engineering had rejected this modification without proper analysis. Harrison stammered something about unauthorized changes and untested variables. The major cut him off. People were dying. If a factory machinist had a solution that showed promise, that solution needed immediate evaluation, not dismissal based on procedural grounds. Coleman made his decision in about 30 seconds. He ordered engineering to conduct full stress analysis of Ray's modification, using the testing equipment and rigorous methodology that Harrison claimed was so important. He wanted results in 48 hours, not theories or excuses. He told Frank to pull Ray off regular inspection duty and assign him to work directly with the test team. He told Ray that if this worked, if his crooked screw actually solved the wing problem, Ray would be compensated appropriately. If it didn't work, well, at least they tried everything before Mustang production got canceled and everyone lost their jobs. The next 2 days were the longest of Ray's life. Engineers subjected his modification to every test they could devise. They mounted wings to modified fuselages and stressed them to destruction. They used X-ray equipment to examine the internal structure. They built mathematical models, ran calculations, consulted with metallurgists and stress analysts. Ray watched all of this from the sidelines. a blue-collar machinist surrounded by men with engineering degrees, wondering if his simple idea would survive scientific scrutiny. He had no illusions about his own education. He had finished 8th grade before going to work in his father's machine shop. Everything he knew about metal came from experience, not textbooks. These engineers had forgotten more theory than he ever learned, but theory and reality didn't always agree, and Ray trusted reality more. The results came back on a Thursday afternoon. Harrison delivered them personally to Coleman's office, and his face told the story before he said a word. The modification worked. The offset screw, placed at a 30-degree angle, created what engineers called a redundant load path. When the wing flexed under G-forces, stress distributed between the primary bolt and the support screw instead of concentrating at a single point. This distribution reduced peak stress at the primary attachment by approximately 40%, enough to prevent the kind of fatigue cracking that had been plaguing production. Computer modeling, still a new and exotic tool in 1944, predicted that wings with Ray's modification would last 3 times longer under combat stress than wings with standard attachments. Flight testing would be necessary to confirm all this, but the preliminary data was overwhelmingly positive. Harrison admitted, with obvious difficulty, that he had been wrong. The modification violated conventional design principles, but it worked anyway, and sometimes empirical results trumped theoretical objections. He recommended immediate implementation across the entire Mustang production line, with Ray's offset screw becoming standard on all new aircraft and retrofit kits prepared for planes already in service. Coleman approved everything on the spot. Within a week, engineering drawings were updated, manufacturing procedures revised, and every worker trained on the new assembly process. Ray's stupid screw became official. The impact was immediate and dramatic. Stress crack failures dropped to nearly 0. Wings that would have failed after 100 flight hours now lasted for hundreds more. Pilots reported that their aircraft felt more solid during high G maneuvers, more responsive, more trustworthy. The modification added less than 2 ounces of weight and cost about 15 cents in materials, but it transformed the Mustang from a fighter with concerning structural issues into the most reliable long-range escort in the American arsenal. By December, every P-51 rolling off the line incorporated Ray's design. By January of 1945, retrofit kits were shipping to every Mustang squadron in Europe and the Pacific. By war's end, over 15,000 fighters had been strengthened by a crooked screw that a machinist invented because he paid attention to what metal was trying to tell him. Ray received a bonus of $500, an enormous sum for a factory worker, plus a formal commendation from the Army Air Forces. North American offered him a position in their engineering department, which he politely declined. He was a machinist, not an engineer, and he was happy staying on the factory floor where he belonged. They compromised by making him a senior technical consultant, a job that let him keep working with his hands while also reviewing designs and offering suggestions. He stayed at North American until the plant closed in the 1960s, training new machinists, solving problems, teaching people to listen to what metal was saying. The story of Ray's screw should have become famous, but it didn't, not really. A few technical journals mentioned it in articles about wartime innovations. Some engineering textbooks used it as an example of empirical problem solving, but Ray's name faded from the narrative, replaced by generic references to improved attachment design or enhanced structural protocols. That was fine with Ray. He never wanted fame. He just wanted to build things that worked, that kept people alive, that did their jobs without failing. He thought about this sometimes in his later years, sitting in his small house in Burbank, reading about aerial combat in books written by historians who never mentioned stress cracks or attachment bolts, or the thousands of small decisions that determine whether planes survived combat. The grand narrative of the war focused on strategy and leadership, on generals and politicians, on dramatic battles and turning points. Nobody wrote about machinists working night shifts, about the quiet competence of people who fixed problems instead of taking credit. That was how it should be, Ray thought. The real work of the world got done by people nobody remembered, people who just did their jobs and went home and didn't need parades to feel satisfied. But sometimes, late at night when sleep wouldn't come, Ray allowed himself to think about the pilots who came home because their wings didn't fail, The missions completed because fighters stayed in the air, the bombers that reached their targets and returned safely because Mustangs kept them protected. He thought about his nephew Danny, who survived 35 missions over Germany and came home to Indiana and started a family and lived to see his grandchildren. Ray never told Danny about the screw, never mentioned his role in strengthening the fighters that protected Danny's bomber. It would have sounded like bragging, and Ray wasn't built that way. Frank Brennan knew, though. Frank, who had taken a risk on a machinist's crazy idea when everyone else said no. Frank, who documented the test results and forced the brass to pay attention. Frank retired a few years before Ray, moved to Arizona for his health, but he stayed in touch. They wrote letters, talked about factory gossip, remembered the old days when everyone thought Mustang production would collapse, and they somehow pulled victory from the jaws of disaster. In one letter, written in 1973, Frank told Ray something he had never shared before. After the war, Frank had tracked down the families of 17 pilots who died in Mustangs before the modification was implemented, pilots whose wings had failed during combat. He never contacted those families, never told them what he knew, but he kept their names in a notebook as a reminder of why taking risks and challenging authority sometimes mattered more than following procedures. Ray understood. He kept his own list, not of the dead, but of the squadrons that received retrofit kits, the units whose maintenance logs showed 0 wing failures after the modification was installed. The numbers were his own private memorial, proof that small acts of competence could ripple through history in ways nobody planned. The engineering establishment never fully acknowledged what Ray's invention represented. To admit that a machinist with an 8th grade education had solved a problem that stumped teams of trained engineers was to question the entire hierarchy of expertise that governed industrial production. So they framed it differently in their reports and analyses. They called it an empirical optimization, a field modification that revealed unexpected stress distribution benefits. They published papers analyzing why the offset screw worked, creating mathematical models that proved what Ray had intuited from experience. They were right to do this, in a way. Understanding why something worked was important for applying the principle in other contexts, for teaching future engineers, for advancing the science of structural mechanics. But the understanding came after the solution, not before, and that sequence mattered. Ray understood this too. He never resented the engineers for claiming credit, never felt bitter about being written out of the story. His contribution was in the metal, in the wings that didn't fail, in the pilots who came home. That was enough. More than enough. In 1982, when North American Aviation's successor company published a corporate history celebrating 50 years of innovation, Ray's modification rated 3 sentences in a technical appendix. His name wasn't mentioned. The author credited unnamed factory personnel with identifying and resolving structural issues during wartime production. Ray read those 3 sentences, smiled, and put the book on his shelf next to his commendation from the Army Air Forces. Both documents were true in their way, and both documents missed the point. The point was this: complex systems failed in ways that calculations couldn't always predict, and fixing those failures sometimes required people who understood the materials at a level deeper than mathematics. Ray's father had taught him to listen to metal, to feel stress concentrations through his fingertips, to trust his instincts when something looked wrong, even if he couldn't explain why in engineering terms. That knowledge, passed from a railroad machinist to his son in an Illinois workshop, ended up strengthening the most famous fighter plane of the Second World War. The transmission of practical wisdom across generations, the value of hands-on experience, the importance of letting skilled workers contribute to design instead of just executing plans created by others. All these lessons were embedded in Ray's crooked screw. But lessons that challenged institutional hierarchies rarely got taught in engineering schools or celebrated in corporate histories. Ray died in 1994, 2 weeks after his 88th birthday. His obituary in the Burbank newspaper mentioned his 50 years in aerospace manufacturing and his work on the P-51 Mustang program. A few former colleagues attended his funeral, old men who remembered the night shift at Inglewood, who had witnessed the stress crack crisis and Ray's improbable solution. They told stories about Frank Brennan's courage in letting Ray try his experiment, about Harrison's furious objections, about the Army investigators who forced engineering to take a machinist seriously. They raised glasses in Ray's honor and agreed that the world had lost one of the good ones, a man who made things better without making a fuss about it. 3 months after Ray's funeral, a researcher working on a documentary about Mustang development found references to the attachment modification in North American's archived engineering reports. The researcher tracked down Frank Brennan's son, who still had his father's old notebooks, including the test data from Ray's first experiment. The documentary aired on the History Channel in 1996, a 60-minute program about the P-51's evolution from a good fighter to a great one. Ray's story occupied about 4 minutes of screen time, illustrated with period photographs of the Inglewood plant and interviews with aviation historians explaining the technical significance of the offset screw. It was a small recognition, decades too late to matter to Ray, but it ensured his name entered the historical record alongside the aircraft he helped perfect. Today, if you know where to look on a P-51 Mustang, you can still see Ray Doyle's contribution. Just below the wing root, offset from the primary attachment bolts, there's a small screw angled at 30 degrees that serves no obvious purpose to casual observers. Restorers sometimes ask about it, wondering if it's a later addition or some kind of reinforcement added during the aircraft's service life. Knowledgeable mechanics explain that it's original equipment, part of the design from late 1944 onward, a modification that solved a critical structural problem. Some mechanics know the story behind it, about the machinist who trusted his instincts over engineering orthodoxy. Most don't. The screw is just there, doing its job, keeping wings attached to fuselages, a small piece of metal that represents something larger about how problems get solved when institutions allow competence to matter more than credentials. The war that Ray helped win from a factory floor ended 79 years ago. The men who flew the Mustangs are mostly gone now, along with the men who built them. The great factories of wartime production have been demolished or converted to other uses. But the aircraft survive, preserved in museums and private collections, still capable of flight, still beautiful examples of engineering and craftsmanship. When those Mustangs fly at air shows, when their Merlin engines roar and their wings cut through the sky, Ray Doyle's crooked screw is there, holding everything together, proving that sometimes the best ideas come from people who work with their hands and trust what they feel more than what they're told. That's his legacy, modest and profound. A reminder that ordinary people doing careful work can change history in ways that nobody expects and everyone forgets until someone takes the time to remember.